Hello guys, we hope that you're doing well and staying safe. For this video, we'll be discussing some examples on surface integrals of scalar fields. So to start, let f be a scalar field of the variables x, y, and z, which is continuous on a smooth surface S. So the surface integral of f over S is defined here by this expression equal to this given limit, provided that this limit exists. So we ask, when do we need to set up an expression of this form, or what are its applications? So for the first one, this surface integral actually gives us the mass of the surface S, given that its density function is the function f of x, y, and z. And if in case f of x, y, and z is equal to 1 for each point x, y, z on the surface, then the mass of S is simply equal to its surface area. So computationally, um, we can divide our discussion into two. So one would be when S is given by a parametrized surface, or is given by a certain parametrization, while the other would be if S is given by a certain Cartesian equation. So first, if S is parameterized by the vector function R in terms of the parameters u and v, where u and v are inside a parameter domain D, then this surface integral is equal in fact to a double integral over the parameter domain of f in terms of u and v. So that is, for the x, y, and z components, or x, y, and z variables, we'll be using the x, y, and z components of the vector function r, while d sigma for this case is actually replaced here by the norm of ru cross rv multiplied now by dA. So again, take note that for this case, this portion dA is replaced either by du dv or dv du, depending on what type of region do you classify the region D. So similarly, if in case here that S is parameterized, or is in fact given instead by a Cartesian equation z equal to g of xy with projection r onto the xy plane, then the surface integral of f over S d sigma for this case is replaced now by the following. So we're taking instead a double integral over r, which is the projection onto the xy plane, and we write f of xyz d sigma in terms of x and y. So here, since z is equal to g of xy, then we could write z in terms of x and y, so we replace it by g of xy, while d sigma for this case is replaced here by the square root of 1 plus g sub x squared plus g sub y squared dA, where g sub x and g sub y represent, recall, the partial derivative of g with respect to x and y respectively. So you could take a look at the derivation once again uh, on the lecture slides. But as an analog, you could take a look as well as at the surface S using the Cartesian equations y equal to g of xz and x equals g of yz. So for that case, since we could write y in terms of the variables x and z, then it should make sense as an analog that we project instead onto the xz plane, while if we could write x in terms of y and z, that is x is equal to g of yz, then we would like to project onto the yz plane instead. So if instead we have y equals g of xz with projection r onto the xz plane, then we write this surface integral in terms of x and z. So that is, f now is written in terms of x, y is in terms of g of xz, and then z is written. And we replace here d sigma by the square root of 1 plus g sub x squared plus g sub z squared. Alternatively, if x is equal now to g of yz with projection r onto the yz plane, then we'll write x now in terms of g of yz retaining y and z, and d sigma is replaced instead by the square root of 1 plus g sub y squared plus g sub z squared. So we proceed now with some examples. So again, we have two applications, the mass and the surface area. So for the first part, let's evaluate here the following surface integrals, beginning with the surface integral of xyz over S, where S here is given by this parametrization, where u is in between 1 and 2, while v is in between 0 and pi over 2. So for our solution, again, our goal here now is to write x, y, z, and sigma in terms of two variables. So since we're given a parametrization, r of uv, then we'll compute for the norm of r cross ru cross rv. So to compute now, r sub u or the partial derivative of r with respect to u is given by cosine v, sine v, and 3 for the first three components, while r sub v instead, taking the partial derivative of each component with respect to v, so that would be negative u sine v, u cosine v, and then 3u has no v, so this is 0 with respect to v. In which case, computing now for the cross product, ru cross rv, this is equal now to the following. So for the first component, we'll have here sine v times 0, which is 0, minus 3 times u cosine v. So we have here 3u cosine v, a negative. For the second component, we have here cosine v times 0, which is 0, minus 3 times minus u sine v. So that would be 3u sine v. But we negate the second component, so this is minus 3u sine v. Well, for the last component, what we have here would be cosine v times u cosine v, which is u cosine squared v, minus sine v times negative 3u sine v is negative u sine squared v. And so we have here plus u sine squared v. Or that is, we could write this now as negative 3u cosine v for the first component minus 3u sine v for the second component. And the last component, once we factor out u, you have here u times cosine squared v plus sine squared v, which is 1. Or that is, what we have here is that the norm of ru crossed with rv is equal now to the square root of negative 3u cosine v quantity squared plus negative 3u sine v quantity squared plus u squared. And so to simplify here, this is equal now to the square root. I'll factor out here 9u squared from the first two terms. So meron tayong 9u squared times cosine squared v plus sine squared v plus u squared. But cosine squared v plus sine squared v is 1. So this is equal now to the square root of 10u squared, or that would be square root of 10 times the square root of u squared is absolute value of u. But take note here that u is from 1 to 2. So the square root of u, the absolute value of u is actually u. Thus, compute now. The surface integral over S of x, y, z, d sigma is now equal to a certain double integral over the parameter domain. You could have here u, v, vu. You could take du, dv. Since both of them are constants, you could take as well dv, du. So let's proceed instead with du, dv. If I have here u is in between 1 and 2, v is in between 0 and pi over 2. X times y times z, I have here u cosine v is x, u sine v is y, and then z is 3u. And d sigma is replaced once again by the norm of ru cross rv, so that would be u square root of 10. Again, we're integrating first with respect to v and then next with respect to u. Or this is equal now to the integral from 1 to 2, the integral from 0 to pi over 2 of, you have here u to the fourth times 3 square root of 10 times cosine v sine v. So notice, 3 square root of 10 u to the fourth is constant with respect to v. So we're taking here this constant with respect to v multiplied by the antiderivative of cosine v sine v. So by a simple substitution of sine v, say w equals sine v, cosine v dv would now be dw. So this is basically w dw, whose antiderivative is w squared over 2. So this is equal now to the integral from 1 going now to 2 of 3 square root of 10 u to the fourth times sine squared v over 2, evaluated from v equals 0 to v equals pi over 2. And then we integrate next with respect to u. And so this is equal now to the integral from 1 going to 2. When v is pi over 2, sine v is 1. or sine pi over 2 is 1. So you have there 1 half. When v is 0, sine v is 0. So this is equal now to 3 halves times square root of 10 u to the fourth du. So integrating with respect to u, we have here the integral from 1 going to 2 now will be 3 square root of 10 u to the fifth all over 2 times 5. So this is 10 evaluated from 1 going to 2. And so we have now our answer. So this gives us 3 square root of 10 over 10. Evaluating u to the fifth at 2, we'll have here 32. U to the fifth evaluated at 1 would give us 1. And so this is equal now to 3 square root of 10 over 10 times 31, or that would be 93 square root of 10 all over 10. So that would be our first example for this topic. If you have any question, you may feel free to rewind the video or pause and then comment down below. If you have none, let's proceed with our second example. So for this case, let's evaluate here the surface integral of the square root of 4x squared plus 4y squared plus 1 over s, where s is the portion of the paraboloid z equals x squared plus y squared below the plane y equals z. So for this example, let's take a look first at our surface of concern. So notice, we're concerned here with only the portion of the paraboloid z equals x squared plus y squared, which is below the plane y equals z. But mainly, we're taking a look here at this surface S. So the plane being below the plane y equals z actually serves as a restriction more on the region R of integration later on. So for this case now, again for our solution, take note that S is actually the paraboloid z equals x squared plus y squared, just below the plane y equals z. So to sketch here, um, if for example this is the positive z axis, say this is the y axis, and then you have here the x axis. To sketch, um, I'll only proceed until z equals 1. So when z equals 1, I'll have here a trace x squared plus y squared equals 1 for the paraboloid. So what we have would be, for example, this is until 1. So what we have here would be something like this. However, we want here the portion below the plane z equals 1. Notice here that when y is 1 and z is 1, just this point, x is already 0. So when y is 1 and z equals 1, that lies on this plane y equals z. So for that case, this lies along this portion. And then since y equals z is technically a cylinder, since it's missing an x variable, then this line, which is its trace on the yz plane, is actually extended forward and backward. So notice, um, none of it would actually hit this portion, or none of the extension of the line y equals z would hit this portion. And so we're mainly concerned with that on the positive y-axis side. So if you extend this line forward, you'll hit this portion, and this surface. And then going backward, what you'll hit will be this part. So what you have here is something like this, something that looks like a cup. So the question now would be, for this portion, what would be its projection onto the xy plane? So again, since we have here z in terms of x and y for our surface, so that is, we could take a look here at x squared plus y squared as our g of xy. It makes sense for us to instead project our surface onto the xy plane. So for the projection onto the xy plane, this would have equation given now by the shadow of this portion, or this portion in fact. So take note here that this is this is the intersection of the paraboloid with the plane y equals z. So its intersection now would be z equal now to y, but z for the paraboloid is equal to x squared plus y squared, or that is, our region R here has equation x squared plus y squared minus y. If we complete the square, the half of the middle term, or the middle coefficient, is negative 1/2. Squaring that will give us 1/4. And then this is equal now to 0 plus 1/4, or that is, we have here x squared plus y minus 1/2 squared equal to 1/2 squared. And so since we have now our surface S as well as our projection, then using our formula, the surface integral over S of the square root of 4x squared plus 4y squared plus 1 d sigma is now equal to a certain double integral over R. Since we're projecting onto the xy plane, we'll write everything in terms of x and y. So since our function, square root of 4x squared plus 4y squared plus 1 is already in terms of x and y, there's no need for us to introduce here g of xy. However, for d sigma, I'll write first 4x squared plus 4y squared plus 1, quantity raised to 1/2. D sigma here is replaced by the square root of g sub x squared plus g sub y squared plus 1, or that is, we're integrating over the region R on the xy plane, the square root of 4x squared plus 4y squared plus 1 times the square root of g sub x, given that g of xy is x squared plus y squared, would be 2x quantity squared, plus g sub y is 2y, and then quantity squared, and then plus 1 dA. Or that is, to continue, we want here to solve the double integral over the region R of the quantity 4x squared plus 4y squared plus 1 dA. Where again, recall here that R has equation x squared plus y minus 1/2 squared equal to 1/4. So that is, we have here, once again, a circle centered at 0, 1/2, whose radius is the square root of 1/4, which is 1/2. So if you notice, it might be better for our case to actually solve this double integral in terms of polar coordinates, since you have there 4 times the quantity x squared plus y squared for the integrand, and you have here a circle as a region for integration. So recall here that x squared plus y minus 1 half squared in polar has equation r equal now to 2 times the radius would be 1 half. And then since it's centered now at 0, 1 half and it touches the origin, then I affix here sine theta, or you have here r equals sine theta. And so to set up now the bounds for integration, this is equal now to, again in terms of polar, you have here 4r squared plus 1. dA is replaced by rd theta. For r, notice that for this case, a strip actually is already inside the region, so our entry here is at the origin, which is r equals 0, while any strip here would in fact exit the portion of the circle, so that would be r going now to sine theta, while theta for this case, for us to generate the whole region, we need here an angle from 0 going now until pi. And so to integrate for the following, we have here the integral from 0 to pi of the integral from 0 to sine theta of 4r cubed plus r dr d theta. An antiderivative for this case would be r to the fourth plus r squared over 2, evaluated from r equals 0 going now to r equals sine theta, and then we evaluate now with respect to theta. And so this is equal to the integral from 0 to pi. When r is sine theta, we have here sine to the fourth theta plus sine squared theta all over 2. At 0, you get there 0 for r to the fourth plus r squared over 2. So in which case, we want to find now an antiderivative for sine to the fourth theta plus sine squared theta. So I'll skip here some steps, but for us to evaluate here the following, I'll recall here the trig integrals. That is, we use here a double angle formula where here sine squared theta, recall, is actually equal now to 1 minus cosine 2 theta all over 2. And if ever needed, cosine squared theta is equal to 1 plus cosine 2 theta all over 2. So apply the following until you no longer have sine or cosine quantity raised to an even power, in which case what you'll obtain here will be the integral from 0 to pi of 5 theta over 8, 5 over 8, I'm sorry, minus 3 cosine 2 theta over 4 plus cosine 4 theta over 8 d theta. And so integrating the following with respect to theta, we'll have here 5 theta over 8 for the first term minus, we have here a linear substitution of 2 theta for this part and then 4 theta for this part. Using a shortcut, we have here 3 sine 2 theta over 4 times 1 half, so that would be over 8 instead, plus cosine 4 theta, antiderivative would be sine 4 theta over 4 and then times 8, so that would be over 32. Then we evaluate this from 0 going to pi. So notice, oops, I have here 2 theta. When theta is equal to pi, sine 2 pi and sine 4 pi are both 0. When theta is 0, all of these are 0. And so this is equal now to 5 pi over 8 minus 0 plus 0 and then minus the quantity 0. So our answer for this item is 5 over 8. Once again, if you have questions, feel free to comment down below. You may pause the video and rewind. We'll continue with our examples on to the next part.